So estimating surds is all about being able to figure out on the number line exactly where a surd might fall. Now, some of the surds we've already come across before, and it's good to know some of the really common surds values. Like, for example, can you remember what the square root of 2 was? About? A bit more than 1. Yeah, I don't know. Was that you saying that? 1.4. Yeah, roughly. But it's not really about knowing those sorts of decimal things. It's about knowing where they lie on the number line. So I'm going to just start off by doing a quick bit of notation work so that you understand what we're doing, and then I'll show you some surds work. So maybe don't write this next thing down. Can someone tell me what that means? Whoops, try that again. What that means? It's less than and greater than. And we can also do that, can't we, as well? That means less than or equal to or greater than or equal to. So remember, this is how I remind my year 7s, but I suspect it's more of a primary school thing, that the symbol is a bit like an alligator's mouth, and the alligator's always hungry, and so the open mouth is always towards the bigger number. Okay, so I can say 2 is less than pi, because the alligator, that was a bad analogy in terms of everyone's hungry for pi, but the alligator's mouth is opening towards pi because that's 3.1 something. Yeah? And similarly, I can say 15 is greater than 1 or negative 1, something like that, or negative 100. Okay, all good so far? So if I want to talk about a value being between two other values, this is the notation I use. Give me a number. 5 is between, give me two other values. 14 and 7. Okay. No, not 7. 3 and 14 then. But thank you for contributing, even though it's a dodgy one. So would you agree if I wrote a number line, that would be how we would write the order of the numbers course? So if I want to mathematically express that a number is between two other numbers, I will put my symbols in like that. So this is 5. The way you can write it is 5 is between 3 and 14. In terms of the less than and greater than symbols, it kind of makes sense. 5 is bigger than 3, reading it that way, and 5 is less than 14, reading it that way. So it's bigger than 3, less than 14, so it's between 3 and 14. Does that make sense so far? This is just a notation thing. Okay, so we're going to now work out a specific example. So, example. Estimate root 7. Okay, that's the example. So, number 1, do I want to do it left and right? Was that useful when I had the example on the left and the instructions on the right, or is it just a waste of time? Is that useful or waste of time? Useful. So work out the closest square numbers either side of, I'll just put 7 here. I'll actually use the example rather than in previous rules. I've tried to sort of make it abstract, but it's getting a bit too complicated to do that. So work out the closest square numbers either side of 7. Okay, so the closest square number to the left of 7 and the closest square number to the right of 7. Okay, so somebody else, thank you, but somebody else who hasn't had an opportunity to talk yet, tell me what the closest square number to the left of 7 would be. Who said that? 4. Well done. Someone else tell me what the closest square number above 7 would be. 9, good. So that means, I wouldn't normally write this, but just for the sake of it, 4 is less than 7 and is less than, 4 is less than 7 and 7 is less than 9. So 7 is between 4 and 9 using that notation. Would you all agree with that? Well, the next step, which is not always true, but in this instance it is, but if that's true, therefore, root 4 is less than root 7 is less than root 9. See how I went straight to an answer then? Are you okay with that? Which means that root 7 is between 2 and 3. Better be. There we go. Oh, you probably can't see that. I'll just hit the calculator button, then it comes up big, doesn't it? Come on. There we go. Square root of 7 is 2.645, blah, 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 blah. So what that allows us to do is, without a calculator, and you won't always have a calculator, say, when you're doing higher order maths. You won't always have a calculator there, but being able to sort of estimate where a surd is on a number line is really useful for doing things like plotting graphs and stuff. So the square root of 7 is between 2 and 3, and we can see it's 2.6, which it's a bit closer to 3 than it is 2, and we kind of expect that, wouldn't we, based upon root 7 being closer to root 9 than it is root 4. All right, anyone got any questions on that? So in practice, I would do, I'll just zoom out so you can see it all at once. In practice, I would do, if I was told to estimate root 7, I would probably do that line and then that line. I wouldn't bother doing that. That's really just the thinking. Okay, let's do a couple more examples. Estimate root 7 plus 3. I won't do instructions this time because it's pretty similar. I reckon you can follow it. So estimate root 7 plus 3. So what I would do is I would put root 7 plus 3 in the middle. And then I would put my greater than and less than sign like so. And again, same instruction. What's the first square number before 7? 4. So I would put root 4 here, but then I would put the plus 3. And on the other side, I would put the root 9 that we had before and put the plus 3 there. And this kind of makes sense because all I'm really doing, guys, is, this is not good for the video, but all I'm really doing is I'm saying root 7 was between these two. If I'm going to add 3 to root 7, I'm just going to shift everything 3 units that way, aren't I? So it's not going to be too surprising that it was originally between 2 and 3. This one is going to be between, square root of 4 is 2. So it's going to be between 5 and square root of 3 is, square root of 9 is 3. So 3 plus 3 is 6. So it's going to be between 5 and 6. Because we just shifted everything 3 units. And again, not good for the video, but I'm just using my spotlight search for this. So square root of 7 plus 3, not too surprisingly, is 5.645. So the same decimal places, just 3 more units up. Any questions on that? Okay, one last example. And then a warning. Estimate 3 root 7. Can't see it, sorry. Estimate 3 root 7. Guess what? It's the same idea. So we put 3 root 7 in the middle with my less than signs either side of it. The closest square root to 7 to the left of root 7 is root 4. So this is going to be 3 root 4 on the left. That's going to be 3 root 9 on the right. And then I simplify that. Root 4 is 2. 3 times 2 is 6. root 9 is 3. 3 times 3 is 9. So we don't have quite as close a range estimation there, but we know it's somewhere between 6 and 9. Is that all making sense? Because we're just scaling it up, right? Again, I'll use Spotlight Search so you can sort of see it. 3 root, oops, try that again. 3 multiplied by the square root of 7 is 7.9, so it's really close to 8, but not quite 8, 7.937. So there you go. It does work. But you can see that when I'm scaling up, so in this case, I'm multiplying, I'm scaling rather than shifting. When I'm scaling up, my range, it's a lot less of an accurate, isn't it? It's a lot less accurate, the estimation. It's now, instead of being between 2 and 3, it's now between 6 and 9. That's 3 whole units difference there. So it's not as an accurate estimation tool really at that point. Now, I've got one warning to give you, but apart from that, does anyone have any questions? Now, I'm not too sure if the booklet has this kind of problem in there, so don't bother writing this down. But if I had to estimate, say, negative 3 root 7, then because it's negative, when I multiply a positive number by a negative number, I'm actually going to get a negative number at the end, aren't I? So what was 2.6 or whatever, root 7, negative root 7 would be negative 2.6. So it's actually shifting it all the way over. So you actually have to root 7, you'd have to put the negative 3 root 9 on that side, because negative numbers, you know, that's more negative, and you'd have to put the negative 3 root 4 on that, so on the other side, right? Because negatives kind of flip everything around, so you're flipping your endpoints there, and that'll give me negative 9 and negative 6. And you can see, I hope, just with a bit of thought, that negative 9 is further down the number line than negative 6. So it does work out. Whereas if I hadn't flipped these over, you'd have negative 6 here and negative 9 here, and that doesn't make sense, because negative 6 is not smaller than negative 9. Okay, I hope that kind of makes sense to you. If it doesn't, I'm happy to follow up. That's enough to get you going with the estimating surds part. But I know, I'm sorry to overload you with theory, but I know that there are some students who have almost finished estimation or onto rationalising. So I need to do a bit of theory around rationalising as well now. So that's your heading, rationalising surds. I'm going to do some basic ones today, and I'll give you some more complicated ones next week. Well, not even next week. Some of you may be up to the more complicated ones. I'll go through that individually with you. Okay, so what do we understand by fractions? We know that with a fraction, so don't write anything down yet. We know that with a fraction, if I have something like 2/7, we know that the 7, the denominator, is how many parts, isn't it? So if I have a packet of Tim Tams and I eat 2/7 of it, what I do is I break down the packet of Tim Tams into 7 equal parts, and then I eat 2 of those parts. Yep. If it's a nice simple packet of Tim Tams which actually has 7 Tim, it doesn't really, it has more, but if it has 7 Tim Tams in it, it'd mean that each Tim Tam would be worth 1 part. If it was a family share pack that had 14 Tim Tams in it, each part would have 2 Tim Tams in it. So if I took 2/7 of the packet, I'd be eating 2 lots of the 2, which is 4. That's how fractions work, right? Even to this extent, that if I went square root of 2/7, it kind of still makes sense, in that we know that root 2 is about 1.4, don't we? So if I broke a Tim Tam packet into sevenths and then ate root 2 of that, that'd be like 1.4 of the 1.4 of one of the sevenths. You know, so it kind of makes sense. It'd be like if there were 7 Tim Tams in the packet, it means I'm eating 1 Tim Tam and then just under half of a second Tim Tam, and then very rudely putting the rest of it back in the packet. Yeah, is that okay so far? So having a numerator that's a square root kind of makes sense. Having a denominator that's a square root is another thing though. So if I went 2 over root 7, what does that even mean? I'm breaking it into root 7 parts. I'm breaking it into parts that contain 2.8 or whatever it was. No, it wasn't that, was it? It was 2.6, something like that. Okay, yeah. But it doesn't make sense, does it, really? Having a denominator which is not a whole number it really doesn't make sense. So what we do is we employ a little tactic to get rid of surds from denominators because conceptually they don't make sense with fraction concepts. It's called rationalizing. Now, if you might remember, we talked about rational numbers a few lessons ago, and I said that surds are irrational numbers. They're non-repeating decimals, non-repeating, non-terminating decimals, and that things like whole numbers and fractions and stuff are rational numbers. So when we talk about rationalizing the denominator, we're talking about turning that denominator into a whole number, effectively. But the concept is called rationalizing. So 1 on root 2. So example 1. 1 on root 2. The steps are 1. Right, is that clear enough? Multiply top and bottom of the fraction by the third denominator. So the denominator here is what? Root 2. So I multiply top and bottom by root 2. I can do that because that is an equivalent fraction, right? I haven't changed the value of 1 on root 2. I can multiply any fraction. If I multiply or divide the top and bottom of any fraction by any number, the result is an equivalent fraction, same value, different look. Okay? So I'm changing what it looks like without changing the value. So 1 times root 2 is root 2. What's root 2 times root 2? Yeah, that's right. Got a few people saying that. Well done. It is now rationalized. Done. So it's really only one step. Okay, let's just make sure. I'm going to give you a slightly more complicated example. It is really only just slightly more complicated. Two on root 7. So what's step 1, please? Somebody else hasn't had a chance to contribute yet? What's step 1? It's exactly the same step. How am I going to make it happen? Perfect. Top and bottom by root 7. And that gets me 2 times root 7 on top and 7 on the bottom. Third example and final example. Oh, was that too quick? You need to finish copying that down? Everyone okay? Okay. Example 3. Step 1. Someone who hasn't had a chance to contribute yet? You just yell it out, I don't care. Yep. Times top and bottom by root 3. That gets me the square root of 24. The square root of 24. Okay, so I multiply the numbers inside the square roots here, in this case, over 3. And yes, root 24 can be simplified because 4 goes into it. So that is, I'll do it in 2 steps. You can do it in your head in 1. So that's root 4 times root 6 over 3, which is equal to 2 root 6 over 3. So you should always try and simplify when you can. I knew what I was doing this time, wasn't a mistake, but honestly, I should have really rationalised that first. That's 2 root 2 there. So if you rationalise first, sorry, not rationalise, if you simplify first, I would have just been going 2 root 3 times root 3 is, 2 root 2 times root 3 is 2 root 6. So it would have been a bit simpler. Okay, where you're headed to, I'm not going to do this now, but know that I need to show you how to do these kinds of ones. If you have something like this, 3 on root 2, root 3 plus root 2, if you have that kind of problem, it requires, you can still rationalize, but it requires a different technique. So as you're going through the booklet, if you get to these sorts of problems and you don't, well, you won't know how to do it unless you look at the example that probably gives it away. But know that I'm going to come back and show you how to do these probably next time we meet. Okay, but if you need to know now, I'll just tell you one-on-one. Any questions? Okay, booklet work. Thanks for being so attentive. And thank you for everyone who contributed, particularly those who rarely contribute and did this time. So thank you. Makes a difference, I reckon.